All right. Well, thanks for switching rooms here. This one's a little roomier. So anybody who's online, if you do want to come to class in person, you're always welcome. We are in S109. It's kind of across the hall, but you got to go around the corner to get to the door. Um, One thing that you do run into in this room, even though we have the TVs here, these might be a little difficult to see once we get to coding and stuff. So one thing you might want to do, even if you're here in person, is join the Zoom session and just turn off your speakers and mic so we don't have echoing all over the place. And I share my screen so you'll be able to see my screen the whole time more closely. Also, the noise you're hearing, they're doing a project on the roof. It's going to be done this week. So, so it's um, you think they would maybe do that the week before classes start, but it is what it is. All right, so share my screen here. Perfect. All right, so we are continuing on our voyage here. So last time I tried to get the point across that everything you think you know about a computer is not necessarily what a computer really is. You spent your entire life using computers, whether it's playing video games or launching software or whatever, not really thinking or having to know what's going on under the hood, right? But if you're going to learn how to tell a computer what to do, you need to learn how a computer actually communicates. And that's kind of what we're trying to close the gap on here. All right. So last class, we talked about all this different number conversion crap. Well, what are we going to use that for? Well, I'm going to try to close the gap here, but I'm also going to tell you it's not like you're going to have to sit there and convert numbers all over the time, all over the place when you're programming. Okay. This is one of those things I want you to appreciate exists. I want you to appreciate that our software is doing all these magical mappings for us. You should know how to do it because it gives you an appreciation for what's going to happen. It'll also help you in your next class, computer organization 325 class, when you will be operating in binary and hexadecimal the majority of the time, and you'll see a little hint at what's going to go on in that class today and here. But effectively, you are learning about a new life form ish, right? Okay, no longer are you going to be problem solving talking to people. Now you're going to be problem solving talking to a computer, and they are just dumb. All right, so I'm going to keep kind of trucking. Last time we did all this number conversion, we saw the two different patterns of going from decimal to any base and then from any base back to decimal. Those two patterns will work regardless of what base we're converting between within base 36, because then we run out of alphabetic letters. Somebody had asked last time, what happens when we go larger than that? Well, you got to have an agreed upon addition of symbols. I jokingly said maybe we just tack on the Klingon alphabet to the end of it, but that's a reasonable thing to do. What a lot of folks do in like these video games I mentioned is they might tack on lowercase letters or the alternative uppercase letters if they've already used lowercase for the front. Typically, we think about uppercase letters as being the representation of the A through Z that we use for representing 10 through 36. But there's nothing that absolutely says it has to work that way. We're just using them as single character representations. All right, now, near the end of class last time, I gave the example. Well, I asked the question of, well, why are we doing base 16? Why hexadecimal? And we used that example. We talked about how addresses work in computers. And typically computer programmers, and most of you are going to fall into this category once we get into C++ here next week. When we start dealing with these things called pointers, which are effectively memory addresses, you're going to immediately be intimidated because hexadecimal numbers look scary. All right. When the reality is computer memory addresses are significantly simpler than the addresses we're all used to dealing with in real life. You know, I use the example, each one of you knows where your house is. 123 Elm Street in a certain city, certain state with a zip code, yada, yada, yada. Now we have the extra stuff on the end of zip codes. So you have to remember lots of pieces of information in order to tell somebody where your house is, the address of your house, right? How many of you are intimidated by that? You don't want to tell people that, well, you probably don't want to tell people where you live, but we've been dealing with normal human addresses for years and years and years and years. So it's not necessarily a scary thing for us, right? We're used to that complex addressing. Whereas in a computer, all the houses, so to speak, are on one big long street. That's house 0, house 1, house 2, house 3, house 4. We just happen to count in hexadecimal. Why do we count in hexadecimal? Because you can represent large numbers in a smaller footprint. That's the punchline. Whether you have a number written in decimal, have a number written in binary, have a number written in hex, they have the same value. We're just representing that value in a different language. The language of binary, the language of hexadecimal, the language of decimal, so on and so forth. They actually ultimately mean the same thing. So the question is like, well, okay, well, we picked base 16 to represent our memory addresses for right now, which is hexadecimal. Well, why didn't we pick base 17 or base 18? Or hey, if using the whole alphabet up is takes us to base 36, and that just gives us plenty of runway for a while to get up to values that large, why not use base 36? Anybody know the answer? Why we chose base 16 as our representation for our memory addresses. And it's going to be the same answer as to why we choose base 8 for some other purposes in a computer. Go ahead. Okay, it is a multiple 2, and what benefit does that give us? Okay. How many of you would enjoy doing the number conversion stuff that we did last class on a regular basis? Interesting enough. Want to do it a couple of times so you can kind of prove to yourself that the patterns sort of work, but it's a little tedious going between some of those different bases and stuff like that. So if certain bases lent themselves to a shortcut, that might be beneficial to us, right? You're going to find that octal and hexadecimal and base 32, which we haven't utilized yet in computing, but once our memory gets bigger and bigger and bigger, that'll be the next hop. When we finally one day upgrade base 16 to have to start using a larger number because that street has more addresses than we can represent in base 16. How many unique numbers can we represent in base 16? Well, we have, base 16 is, we're going to be dealing with a, typically in a computer, it's going to be a 64-bit memory address. Okay, well, in base 16, we have to fit that inside of 64 bits. So it's going to be 2 to some power, 2 to the 31st power, 2 to the 64 power. Those are the number of unique addresses that we can represent. Well, once we have one more house that gets built on the very end of the street, way, 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 way down there, and we want to address that house, we want to say that that's house umpteen trillion, whatever. It'll actually be larger than that. Then we need to upgrade to a larger representation space, a bigger number. And instead of going to base 17, we will go to base 32 for the reason we're about to talk about. All right. So let's see. I just want to see here. Did I do something? Did I convert to base 8 somewhere? It doesn't look like it. So let me just quickly. Let's take a number like 1011 in binary to octal. Now, we didn't actually look at this example last time. This is going to require both patterns, right? We first need to go 1011 from binary to decimal. Then we can go from decimal to octal. So let's play this out as we learned in class last time, and then we'll see the shortcut. Okay. would be really funny if somebody just comes flying through the roof. I'm pretty sure what we're actually hearing is them pulling up the roof is tarred. So I think they're pulling up the tar from the roof. Maintenance emailed me and said that they'll be doing that in the morning. And like, okay, well, maybe early morning. I don't think so. It doesn't seem like that's what's going down. All right. So the first pattern we're going to do is we're going to follow 1011 binary to decimal. Okay. So this is 1, 0, 1, 1. This is the ones place. This is the twos place. This is the fours place. This is the eights place. So this is 8 times 1 plus 4 times 0 plus 1 times 2. Actually, let's stay consistent. 2 times 1 plus 1 times 1. So that's the number 11. And with small enough numbers like this, you can kind of just do it in your head. You can say, okay, this is the ones place, the twos place. So that's a 3. Nothing in the fours place. There's an 8. 8 plus 3 is 11. All right. So you get used to thinking about it that way. All right. So we have 11 now, is the decimal equivalent of 1011. So now we got to go 11.
I have a question.
Yeah, go ahead.
So if we were to include a fifth place, like say 11011, then would that fifth place be 16 instead of 8 because we go from 1 to 2, 2 to 4, 4 to 8, it doubles.
Are you talking about a 1 where I just put it right here, or a 1 in the front?
A 1 in the front with 5 places.
Yep. So this is the ones place, the twos place, the fours place, the eights place. Now this is the 16th place.
So it just keeps doubling.
Correct.
All right. Thank you.
Yep. Because we're dealing with binary. So it keeps going up by a power of 2. If we were dealing with base 8, it would go up by a power of 8. It's, it's 1 to the 8th place, or 8 to the 0's place, 8 to the 1's place, 8 to the 2's place, 8 to the 3's place, where this is 2 to the 0th place, 2 to the 1 place, 2 to the 2, 2 to the 3. One more thing I'll point out here is these two numbers are the same. So it does not matter how many extra zeros you have out front. It doesn't add magnitude because yes, this is the 16th place, but it's 0 times 16. This is 0 times 32, 0 times 64, 128, so on and so forth. And the reason I point that out is, let's say we were going to represent the binary representation of the decimal number 11 as an 8-bit binary value. That means you have to use up all 8 bits. Well, I only need 4 bits to represent the 11. So you would just throw 4 extra zeros on the front, which does not change the value of it, but fills out your 8 bits. Go ahead. 16 goes to 32, then 64, then 128, then 256 as we go left. Oh, well, hexadecimal doesn't double each time. Hexadecimal multiplies by 16 each time.
Why can't we just add another number in front rather than upgrade to the 32 system? Because like you're adding basically twice what you're adding 16 times.
Give me an example of what you are trying to accomplish, and then I'll tell you why you can't do that.
Like eventually we'll have to go to the 32 system because we're like running out of space. Like, can't you just keep putting more numbers to the front?
Yeah, that's what I was saying. Why are we jumping to 32 rather than base 17? Just doing one more base. Is that kind of what you're asking?
Yeah.
Okay, so put a pin in it for 5 minutes. I'm gonna explain. All right, so then ask again if it's still not clear. All right, so let's keep going down this example where we're doing a long-winded way of converting 1011 from binary to octal. All right, this is it's gonna really gnaw at us if we have to do this often, because now we have to do both patterns we learned last class. So we went from binary to decimal first, and that got us the 11. And then we're going to go 11 decimal to octal. So this is our other pattern. So this is 11 divided by 8. 8 goes into 11 one time. 1 times 8 is 8. We need 3 to get to 11. So that's a remainder of 3. 1 divided by 8. 8 goes into 1 0 times. We know we're going to be done once this is a 0. 0 times 8 is 0 with a remainder of 1. So that means that the answer here, we read it from bottom up, is 1 3. That is 1 3 in octal. Make sense? So to go from binary to octal, it took us several steps. All right. So now let's look at an example here. Where am I going? Okay. So let's copy this slide. And I'm actually going to insert another slide in the middle just to show something. So we're going to call this the octal bit space. All right. You'll see what that means here in a second. What are the range of decimal values that octal, what are the range of octets that make up all octal numbers? 0 to 7, right? So we make up all octal numbers with the, we would say digits, but digits is base 10. Since we're dealing with that base 8, these are the octets of it. So 0 through 7 is the values we'll need. So 0, 0, 0, well, the first thing I'd ask is, how many bits, how many binary bits do we need to represent the values between 0 and 7? Good. Well, I could represent it. So like a 0, let's go with a 1. That's a 1. What's a 7? A 7 is that. So we didn't need all the bits there to represent a 7, did we? This is the 1's place, the 2's place, the 4's place. 4 plus 2 is 6, plus 1 is 7. So we actually only needed 3 bits to represent all of the octets. Make sense? We need to represent a 0. So this is a 0. We need to represent a 1. So that's a 1. We need to represent a 2. That's a 2. We need to represent a 3. 3. We need to represent a 4. 4. We need to represent a 5. 5. We need to represent a 6. 6. And we need to represent a 7. 7. Make sense? Okay. Now, the kicker here, the trick here is 3 bits let us fully articulate the entire octal bit space. No more, we could not do it with fewer bits, and we do not need more bits. We are fully representing it. Make sense? Okay. So we go back here, and we're going to take the octal number 13. Didn't I copy the thing? Oh, there we are. So we're going to say 13 octal to binary. We're going back the other direction. This slide said this in binary back to octal. Okay. So let's look at our cheat sheet here that we just created. This guy right here, I need a 1 first. A 1 is 0, 0, 1. Then I need a 3. 0, 1, 1. So That is the binary equivalent. Now, wouldn't you say that that number and this number are the same number? Because those leading zeros we just talked about do not change that value. This is the ones place, the twos, fours, eights. This is 0 in the 16, 0 in the 32. So this value right here, 1011, is the binary equivalent of the octal value 13. 1011. We were able to go between those two without doing any of that division stuff or looking at the places stuff. All we had to do was write the 3-bit representations of each octet. All right. Similarly, if I literally steal this guy and we want to go 1011 binary to octal, I know I need 3 bits to represent an octal octet. So I'm going to rewrite 1011 in groups of 3. 0, 0, 1, 0, 1, 1. Same value, right? I just padded it out to give me groupings of 3. That's the first value. That's the second value. Because again, 3 bits lets us represent all of the octets. So now we just look at it and say, oh, well, that's a 1. And that's a 3. That's the octal value 1, 3. So going between octal and binary is much, much, much easier than doing all that math, right? Wouldn't you say this looks a lot easier than that? Okay. And guess what we're going to find out about base 16? You can represent base 16 using how many bits? All of the hextets in base 16, that is 0 to 15, 0 to 9, A through F. How many bits does it take to represent all of those? Good. Exactly 4 bits. So let's look at that. So we're going to call this the hex bit space. Probably going to do this in 2 columns. So this is 0, 0, 0, 0. That guy's a 0. 0, 0, 0, 1. That's a 1. 0, 0, 1, 0. That's a 2. 0, 0, 1, 1. That's a 3. 0, 1, 0, 0. That's a 4. 0, 1, 0, 1. That's a 5. 0, 1, 1, 0. That's a 6. 0, 1, 1, 1 is a 7. And then let me go over and create my second column here. Now this is going to be 1, 0, 0, 0. That's an 8. Then we're going to have 1, 0, 0, 1. That's a 9. 1, 0, 1, 0. That's a 10. Or an A. 1, 0, 1, 1 is an 11. Or a B. 1, 1, 0, 0 is a 12. Or a C. 1, 1, 0, 1 is a 13. Or a D. 1, 1, 1, 0 is a 14. Or an E. And 1, 1, 1, 1 is a 15 or an F. Make sense?
I got a question.
Go ahead.
Why is hex unable to accommodate letters beyond F?
Well, because it stops at 15. Hexadecimal is base 16, so the legal values are 0 to 15. Just like with octal, the legal, which is base 8, the legal values are 0 to 7. If I went to base 17 instead of base 16, we would be able to accommodate a G for number 16. Base 17 supports the values 0 through 16. Base 18, 0 through 17, so on and so forth. So we would need base 36 to fully utilize the entire alphabet. But what we're seeing right here is with 4 bits, we are representing every single possible hextet, 0 through 15, with 4 bits in its entirety, just like we did with octal. Good.
Do you think we're ever gonna have like, do you think that's ever gonna happen within our lifetime to upgrade to 36-bit? Or is that gonna be something,
Well,
anything like?
You mean to go to the next step of beyond this? Would be 32,
Yeah, 32.
because 32 can be represented in 5 bits.
Like, I didn't know if that's gonna be something like probably only the government, but like supercomputers, like as everyday regular consumers with like our laptops here. Do you see technology advancing that far, that fast?
Yes, but it's gonna bridge, because what's gonna happen is we only need a really big number to represent, if we're thinking about computers, memory that goes way down the line. So for instance, if you use your imagination and say, how much RAM are we ever going to have? How much hard drive space are we ever going to have? So for instance, a huge hard drive today might be a 4 terabyte hard drive for like normal people, right? You can create, a series of things and get, up to 2 exabytes of hard drive space or something like that. But even that, you only need to address each chunk of the hard drive, saying this is bucket 0, bucket 1, bucket 2, bucket 3. And even though that sounds huge, I bet you we can probably accommodate that. Let's see, to the 64th power. That's 18 quintillion. So with a 64-bit number, we can represent that in groupings of 4 in hex just fine. So the real question would be, if we represented that in hexadecimal, how much shorter would it be if we represented it in base 36, for example? The number would compress a little bit, but I'm not sure that gives us a whole lot of benefit squeezing down to that size. Because if we're really looking at why do we choose hex rather than just address our memory with binary? Because we already saw that they're all the same, right? It's just how many 1s and 0s does it take to represent a 13, right? For example, if we were debating between binary and octal, it would be even shorter if we went to hexadecimal. So hexadecimal allows us to represent big numbers in a small footprint. For really, really, really big numbers, we could represent them in a little bit smaller footprint, probably with a base 36. But at what point is that really worth it when human beings rarely see the value? So really, it's going to come down to, when does our computer architecture mandate that we need a larger bit space? And I'm not sure that's going to happen with traditional computers, but it could happen with quantum computing. Possibly. But for right now, the context you should be thinking about in your head is, if I want to write down a really big number, what's the best language to write that in? Do I write it in binary? Well, it's going to be a long bunch of 0s and 1s. Do I write it in decimal? Well, that's going to be comfortable for me, but still, that number right there in decimal is really, really big, right? That's 18 quintillion, I think. So this is thousands. Well, this is thousands, millions, billions, trillions, quadrillions, quintillions. That's 18.446 quintillion. Now we had to like mechanically go and figure out what that number was. That is not a convenient number for us to glance at and see that in hexadecimal. I wonder if this guy can convert between that. So let's get this number. We can do the conversion ourselves. We know the pattern, but I don't think we want to spend the entire class doing that. So decimal to hex converter, here's the decimal number. We have to go to more than 16 bits. This is let it go. We can't do it. We need to have more than 16 bits there to pull this off. Okay, I think this is going to let us do it. So in hexadecimal, that's that number. It's a power of 2. That's why you just have a 1 on the far left and everything else is a 0. So at the very least, that number, and that is a hexadecimal number, even though it's just made up of zeros and ones. It just, that's what it took to make that number. Because this is the ones place, the 16s place, the 256, the 496, the 4096 rather. 16,585 maybe, whatever, just keep multiplying by 16. That's what you get for that value. The very least, that is shorter than that value by at least a couple of spots. Make sense? So we just choose to represent it in hex, even though all of those values, here's the octal version, the hex version, hex bytes is something for character representation. We'll talk about that at some point. This is decimal. Here's binary. We definitely don't want to write it in binary. Binary is a lot of zeros and ones. So we kind of choose hex because it's a relatively concise and, more importantly, compatible format. We're seeing compatible because of this. All right. So we can represent every hexadecimal hextet using exactly 4 bits. Which means BAD hex to binary. We have a B, we have an A, we have a D. We can go to our cheat sheet here and see that a B is 1011. 1011. An A is 1010. And a D is 1101. Put all those together, 1011, 1010, 1101. That is the binary version of the hexadecimal BAD. Make sense? So that's the shortcut. We can conveniently go between octal and binary without making a pit stop at decimal. We can go conveniently from hexadecimal to binary without making a pit stop at decimal. Those two bases are very, very compatible with binary and computers. That's why we picked them. That's why we didn't choose base 17 or base 18. That's why the very next base, the very next compatible base we'd run into is base 32. If we did this same slide for base 32, we would write every permutation of 5 bits. Make sense? Which would take a lot more space, isn't really that hard to do. We would have 11111 is the value 31. Make sense? All right. Which would be whatever the 32nd letter of the alphabet is. I don't want to go through the ABCs, but whatever the 32nd letter of the alphabet is, that's what it would represent. Oh, sorry, not 32nd letter of the alphabet. 32nd, the 22nd. You got to subtract 10 from it. Yeah, because the first 10 values, 0 through 9, we already got those. So we only need the alphabet for the next value. So base 32 would be 32 minus 10, which gives us 22. So the letter, he said it's V, instead of it capping an F. All right. So questions on why octal and hex? I'm not necessarily saying that you're going to have to convert these on a daily basis. But I want us to have an appreciation that that is why we have just arbitrarily picked binary, decimal, octal, and hex as the bases, the numeric bases that exist when communicating between a human being and a computer. Binary is the computer's native language, numeric language. Decimal is our base language. And then octal and hex are convenient conversions between binary and those. We can move between those quickly. All right, makes sense? It's not that there's anything extra special about those bases. All right. Bases conveniently. So what are we going to be like at the end of class once all of these glue, we're done sniffing these glue fumes? If it is destroying you, you can take your laptop and go someplace else and jump on Zoom. I promise I won't be offended, but I'll stick it out here. But you know, all right. So these bases conveniently convert to and from binary. All right. All right. So now, again, we're continuing to think about how are we going to boss this computer around. Now we have an appreciation for computers, or for the numerics behind a computer. Let me ask one more additional question here. So when we ask ourselves, what's a number? We just talked about a whole bunch of different ways of representing numbers, right? So representing the values 0 to 15, for example, is all the hextets, but we represented all these numbers. Well, one thing we use numbers for is for math, magnitude stuff, right? So magnitude, math / how much of something. So we might say something weighs 7 pounds or something like that. All right. But another thing we might do is we might represent, use numbers to just count, to uniquely represent different things. We would never do math for it, but maybe we say that, oh, well, that's item 0, that's item 1, that's item 2, item 3, so on and so forth. Those 0, 1, 2, and 3, it would never make sense for us to say, well, item 2 plus item 3 equals some final number. We just are uniquely identifying things using numbers. All right. So an example of this is, and we're going to get into this in more detail later, but characters in a computer. We've already talked about that computers like numbers. Computers operate in binary. Now, would you rather see a number or the letter A? Human beings prefer characters, right? All right. So what we have is something called ASCII. So that's American Standard Code for Information Interchange. Doesn't matter what it stands for. So ASCII is an 8-bit representation for characters. All right. So what that means is some character is represented by 8 zeros. Some character is represented by 7 zeros and a 1. Some character is represented by 8 ones. Okay, so we have 256 unique characters that can be indexed using 8 bits. 2 to the 8th power is 256, 0 to 255 would be our unique representations. Make sense? So we can choose our favorite 256 characters that are ever written down. That could be all the alphabet, that could be commas and question marks. Notice it says American Standard Code for Information Interchange. So we just assume that English is the only language that means anything. So we actually only use 7 bits to get all our punctuation, everything like that. And then we just started doing like playing cards and smiley faces and stuff like that. We didn't even think about putting other languages in there. Okay, but this is a pretty dated thing. Anybody know what the upgrade to ASCII is? That pretty much is always used today. It's something called Unicode. So the first 256 characters in Unicode is the ASCII character set. The rest of them brings in a whole bunch of other human languages and their characters. All right. And Unicode is a 16-bit representation for characters. So this gives us 2 to the 16th power number of unique characters we can represent, which is 65,536, which means we have 0 to 65,535 are the indexes for all the characters that we may ever want to represent in a computer. As soon as we decide we need more than that, we'll jump to the next base, right? I'm not sure that we'll get to that, but so in that example, you don't need to memorize that type thing, and we'll actually hit this again when we talk about variables next week. But this is an example of an alternative use of numbers. We're not using these to do math. We're using a number to just say, the letter A is actually this guy. He's represented with this number. That way we can tell a computer about the letter A by telling it to hold the number that represents the letter A. And then during runtime, if we know that our software was supposed to represent a character, we'll do that mapping between the number the computer holds and the character we should show on the screen. That'll just happen by our really fast computer while our program is running. Because at the end of the day, all your computers are going to remember is numbers. Make sense?
I've got a question.
Sure, go ahead.
Isn't there a 32-bit range that goes up to like 4,297,000,000?
Yep. So like we're going to talk about that when we talk about integers. So 2 to the 32nd power is 0 to like 2.1 some odd billion. So yeah, but you know, so your question might be, well, why didn't we have a Lippmann character set that is a 32-bit representation for characters? Right? That's kind of what you're asking. Why didn't we just jump to this?
Pretty much.
Okay. Well, so there's not a great reason why we couldn't have. The real question is what are we trying to represent? First of all, if we're using 32 bits in our computer to remember a character, that's 32 zeros and ones, 32 bits of memory that our computer is dedicating to storing a character. Well,
and that's a lot, right?
That's a lot. Well, okay. Whether it's a lot depends on time. If we go back to, 1970s, that's a lot. By today's standard, it's nothing. But it's still something if you have a zillion characters you're storing. So the real question is we want to be good stewards of our memory, and we want to have enough bits to represent all the stuff that we need, but we don't want to just arbitrarily say, well, I'm going to use 32 bits to represent all the characters and human language, where we might decide, well, is there actually 2.1 billion characters? And actually it's 4.2 billion. So 2 to the 32nd power is 4 point something or other billion. 2 to the 32nd is 4.294 billion. The reason I said the 2.1 billion is because typically we store positive and negative numbers.
Yep, that's it.
So we have to represent both directions. And that is now more about doing math with it. And we'll talk about that when we get into talk about integers and stuff. But for this punchline here, I effectively can represent 4.294 billion unique characters with a 32-bit value. So we would ask ourselves, is there 4.294 billion characters in the human language, or things that are close to the human language, that we might want to represent? Probably not, right? So right now we've capped ourselves at 16 bits, which is 65,536 unique characters. And we pretty much have fit what, the scientists would say is all of the characters that matter. in there, right? So I'm sure there are some languages somewhere that we've just determined aren't important enough to represent in a computer in Unicode, and we just don't represent them. But it covers all the major ones and then a whole bunch of minor ones. So the answer to your question is there's not a great reason why we can't jump to 32. We just don't need that many unique characters to be represented. So why use extra computer memory to store it?
Right, makes sense.
And these things, I know we're like talking about bits and flying around and all this stuff. As we go through the course and as you see the context of these things, how it keeps popping up in all sorts of different parts of communicating with the computer, whether it's where we're storing something in memory, that address on the street, or whether how we're representing a character. We're going to keep seeing that same pattern over and over and over again. So really what I want us to get out of this is an appreciation for computers like binary numbers, human beings like decimal numbers and characters, and we have to have a way of moving between those two without us being inconvenienced because we're lazy. That's the punchline of all this. There is going to be software that lives between us and all this number crap such that we don't actually have to do it. But we're computer scientists, so we want to understand how it's working because sometimes having that knowledge will allow us to do some pretty powerful things. I think last class I probably mentioned something like you can solve 80% of the problems with a rudimentary skill set. You don't have to know about all this under the hood stuff. It's that last 20% that unless you're leveraging this level of knowledge about what's actually happening, you won't be able to solve those last 20% of the problems because that's where kind of unique human problem solving really comes in, where you're kind of having to create a very bespoke solution to a particular problem using either a math trick or some kind of bit space trick where you use the second half of one number and the first half of the next number to produce a new number, stuff like that. And you'll talk about that more in here, and you'll also look at that kind of stuff in the 325 class. All right, so really we could keep going with this slide and basically say, what are other uses for numbers? But two uses is good enough. We can do math with it, and we can also use it to uniquely identify things. Make sense? All right, so a number isn't always a math thing is the point. We use numbers to do different types of things, so we're not always going to be adding a number to another number if we're using it to uniquely represent something. All right, so we already answered the question of why octal and hex. All right, so let's just kind of close the gap on something we were talking about last class. We're talking about different types of languages. So we already talked about machine language. Computers like zeros and ones. Everybody's cool with that? Not our cup of tea. We don't want the 2-button keyboard, but we can all deal with the fact that computers like zeros and ones, and we need to put layers between us and the computer for us to tell this guy what to do without dropping down to his stupid 0 and 1 level. We want to stay up here at the human smart level as long as we can, right? And only get into the weeds as much as we absolutely have to. But we want to understand the weeds. All right? So then we have this low-level language. Now, last class we talked about CPUs, right? And we mentioned that a CPU is effectively a collection of magic tricks. We did that little exercise where, you're moving your hand in different ways, and you got these little simple hand movements, but you put enough of them together in the right order, you can accomplish real tasks, right? So we can think of like our arm as a CPU that has these 20 magic tricks, 20 things the arm can do. And if you can just give a list of movements in a row, you can, through trial and error, accomplish real tasks by telling the arm to do this, then that, then that, then that, then that. Everybody cool with that? All right. So a low-level language is the equivalent of that for computers. So a CPU has this big list of thousands of magic tricks it knows how to do. And we represent those as this is magic trick 0, magic trick 1, magic trick 2. We are indexing the magic tricks, just like we were indexing Unicode or ASCII or whatever. All right. So they have all these different magic tricks, and we're going to keep track of which magic tricks we're currently dealing with using a low-level language. So a low-level language has a one-to-one relationship with the CPU. Okay, it's closer to English than zeros and ones because we don't like the zeros and ones, but it's still not so much cryptic enough, but it's detailed enough that human beings still aren't going to like it. So every line of code we write in a low-level language translates into exactly one line, one magic trick on the CPU. Make sense? All right. So that's what a low-level language is. This is, I mentioned a few minutes ago, we need to create layers between us and the computer. So one layer there is this layer called a low-level language. Usually it's assembly language is the language that we work with. That's a low-level language. Okay, we understand it exists. We would like to write assembly code as little as possible. We would want one of our other tools to write that assembly code for us. Because really where we want to spend our time as computer programmers is at the high-level language level, where we write one line of code and it translates into a whole bunch of instructions to the CPU, a whole bunch of magic tricks on the CPU. And some piece of software that's already been written does that conversion for us. All right, makes some sense? All right, so those are the different kind of classifications of language. Human beings want to live here. Computers already live here. This is kind of our intermediate thing, but human beings want to spend most of their time writing this stuff and then getting it automatically converted here. So now let's look at some examples of this low-level language. All right, so here's an example of an assembly language instruction. There's really two instructions, okay? So imagine we are on a processor, and a processor is this collection of magic tricks. One of these magic tricks is the magic trick called move. We are moving a value from one hardware register, BX is like a storage location on the processor, into another hardware register, another storage location in the processor. So this moves the context of whatever's in BX into CX. These are places. BX and CX are places on the processor, little memory locations. Then as a second command, we want to then add AX to CX, storing the result in CX. That's another magic trick. The CPU knows how to add stuff. If I give it two values to add, it will add the first value and the second value and overwrite the location of the first value with the sum. Okay? So two magic tricks. CPU knows how to move stuff between one memory location and another. CPU knows how to add stuff between add two values together, storing the result in the location of the first value. That's just two magic tricks that might exist on a CPU. All right. Now, as human beings, we can look at this and not immediately run away screaming. It's English enough looking that like, okay, well, this is moving something from one place to another. Okay, I can pretty much wrap my head around it after it's explained to me. This guy, if I asked you to guess what the add magic trick does, you could probably come up with it probably adds stuff together. Okay, not a huge leap there. Okay, but under the hood, inside of the computer, all of those instructions are indexed. So the equivalent of move CX BX is this guy. This is the binary equivalent of the move command. This is the ones place, 2s, 4s, 8s, 16s, 32, 64, 128. So this is 128 plus 8. So that's 236, 237. So the move command is magic trick 237 on the CPU. That's what magic trick it is. So we're saying call magic trick 237, which the computer then goes and looks up and says, oh, that's the move command. And this guy over here represents a combination of the two hardware registers. So part of that number is the AX, part of that number is the BX or the CX and in there. All right. So ultimately, if we were talking machine language to the computer, we would feed it that string of zeros and ones, followed by this string of zeros and ones. None of us want to do that. It's cool to look at and for 5 minutes appreciate that that's ultimately what's happening. At the end of the day, that's what gets sent to the CPU. Oh man, that's awesome. All right, so at the end of the day, that's what gets sent to the CPU. Similarly, that second command is going to send that to the CPU. So we would certainly rather write something like this over something like this. But we'd really prefer to write something in a high-level language that looks more English-like, where we don't have to do 2 lines of code to do something as trivial as adding 2 values together and store the result. All right? All right, so let's gain an appreciation for what these high-level languages are doing for us. What we're looking at here is the assembly code needed to write a single character, one character, like the letter A or B or C, this is the letter A, to the screen. Imagine if we're writing a whole sentence. You would need to repeat this code for every single character in that sentence. How many of you would want to write that by hand? All right, so doesn't matter what all this is doing, but what are we doing? We're moving some value into this hardware register. We're moving another value into this place. This is another special kind of register on the CPU. We're moving a value here. We're moving A into here, and it's going to convert A into its ASCII equivalent. You know, so the binary version of the letter A. We're going to move this value into AH. AH and AL, this is actually the AX register. One's the high part of it, one's the low part of it. So the AX register is a 16-bit register. AL is the first 8 bits. AH is the second 8 bits. Not something you need to know in here, just kind of filling in the gaps of what's going on here. All right. So we're doing all these little ninja moves, right? And then ultimately here at the very end, we're stopping the CPU for this to actually appear on the screen. Effectively, we're putting this onto the graphics card, something called the frame buffer, where ultimately we'll put an A on the screen. Then I need to go to the next letter in my sentence, then the next letter in my sentence, next letter in my sentence. This is if we rolled back to the very, very, very early days of computing, if we were writing assembly code to talk directly to a processor. So this is the lowest level programming you can get to without speaking in zeros and ones. All right. So we can look at this, we can appreciate it and say, okay, well, that's all fun if I watched it on the History Channel, but maybe that's not what I want my career to be. Okay. So now we throw in the idea of an operating system. What's an operating system? Well, most of you are used to using operating systems, right? None of you sit there with at your computers with, you know, little metal pokers and you're touching 2 pins together and stuff like that, right? You sit at a keyboard, you're using Windows, Mac OS, Linux, something like that. Now, actually, none of those are actually operating systems. They're all distributions. The actual underlying operating system for Windows is the NT kernel. Modernly, that's a new technology kernel. Years ago, you had 2 competing things from Microsoft. You had DOS, then DOS became the 9X kernel. And then, then they introduced the NT kernel. NT kernel was for business. Those kept growing, 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 and eventually they merged together with Windows XP. And since Windows XP, the NT kernel has survived, the 9X kernel disappeared. So now whenever you run DOS in the command terminal or something on your computer, it's emulating it. But the actual underlying operating system for Windows is the NT kernel, KERNEL. For Mac, do you know what the underlying kernel is? Underlying operating system on a Mac OS X? It's OpenBSD Unix, the Unix kernel. For Linux, it's the Linux kernel. Before Mac OS X, the first rendition of Mac OS X, we had Mac OS 9. Its behind the scenes was DOS. and then what Apple was given by Xerox years ago when Xerox decided real money's in copy machines instead of computers. Very early days of computers, Xerox was working on their own graphical user interface computer controlled by a mouse. They gave up on it and gave it all to Apple. So that's where the first Mac came from. All right. So what is an actual operating system? This is a layer that sits between the human and the, we're going to say the CPU rather than just say the computer, but it really is the entire computer. All right. So that we can accomplish some advanced tasks with fewer human written instructions to the CPU. Why? Pun intended here. Humans like power tools. True statement, right? If you're doing something around the house, would you rather use a manual screwdriver or one of those, you know, if you're not doing anything big, heavy duty, you will have one of those battery operated kind of, you know, screwdrivers that makes screwing screws in and out faster, right? If you're working on something where you're screwing boards together, whatever, you might use one of the more powerful power tools. Otherwise, you just blow right through your wall. I've done that. But you get the point. We try to interject into our lives anything we can do to make things easier. So we like power tools. All right. So an operating system is effectively a power tool that human beings invented. So some smart humans years and years and years ago had our first operating system, which said, hey, what are some of the things that a human being might ask a computer to do? For example, do you think it's pretty common that a computer will display some text on the screen? Pretty common occurrence. So might it make sense for the writers of the operating system to solve that hard problem once, include it in the operating system, and then for them to provide what are usually called system calls in the operating system that will write something to the screen? Does all that heavy lifting for you. You still got to do a little lifting. So let's look at that. So our proverbial first program usually is a program called Hello World, right? This is just some computer program that displays Hello World to the screen. This is Linux assembly. So this would be, when we're dealing with assembly code, we actually have to target two different things. Assembly code targets CPU architecture and operating system. Because if you're going to assemble your assembly code and you intend on using some of these power tools built into the operating system, the assembler needs to know that you are writing assembly code, maybe for the Intel processor, but specifically for the Linux operating system, or for the Windows operating system, or for the Mac operating system. Because even though assembly language all look very similar, those built-in system calls, so like in Linux, it's called syswrite, might be called something a little bit different on Windows, or it might be a different magic trick number in the operating system. So really, when you're assembling something, you have to target two different things. What kind of processor am I talking to? So you choose the right assembly language. And then what power tools do I have available to me? So what we're looking at here is the Hello World program written in Intel assembly, x86 assembly, specifically for the Linux operating system. All right. So what we want to do, forget about these things kind of over here. This is just showing you kind of equivalent high level code. What we're really doing is looking over at this left portion. So to display the entire word, entire sentence, hello world, to the screen, instead of one character at a time like we saw, one character at a time took basically the same amount of code instead of displaying an entire thing. So let's just look at how it actually works. Notice these first four things. We are doing four ninja moves. Okay, we're calling the same magic trick 4 times in a row, but we're moving different things into different places. Make sense? So we're going to see actually how assembly language works with the operating system. This is how all modern programs work, since everything now runs on operating systems, right? So we're going to move the value 1 into this location. And this value 1 represents the system call. So system call 1 is syswrite. It's what's built into Linux for writing stuff to the screen. This next one, we're moving the value 1 into this location. This guy is, where are we writing it to? Are you writing it to a file? Are you writing it to a printer? Are you writing it to the screen? 1 is standard output, which is the screen. Then we're moving this value here into this location. This is the what are we writing, the message. And notice down here, we've defined a variable, defined a memory location called MSG that holds hello world. All right. And these are in bytes. This is a bunch of data bytes because this is ASCII for H, ASCII for E, so on and so forth. Okay. This last one, we are moving the length of that message into this location. The length of this guy is stored inside of message length. So in this case, it'll be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. It'll be 13 bytes long. Okay? Because really what you're telling it is where in computer memory does your message start? And then how long do you want me to keep displaying stuff to the screen until I hit the end of the message? That's why we need to know the length of it. All right? So with these first 4 lines of code here, all we're doing is staging some values into 4 different memory locations, because those 4 memory locations are going to be used by the syswrite system call of Linux to actually display something on the screen. So you're moving the, what do you want to do, syswrite, to one of them. Where do you want to write it? What do you want to write? Where's the beginning of what you want to write? And then how long should I keep going? How long should I write? Then you call upon the operating system. So all we do is we store 4 things in 4 very special places. And what the operating system will do right off the bat is they'll come right here to RAX, this location, and it'll say, what is it that you're trying to do? And they'll see, oh, you're trying to do magic trick number 1, operating system magic trick number 1, which happens to be syswrite. Okay, well, if that's what you want to do, I'm going to need 3 pieces of information for you. Where do you want to write it? What are you writing? And how long is it? Because it needs 3 things for that function, for that ability, we have provided it 3 things that it knows where to go. So we have to store those 3 things in specific locations. So the operating system will start here, say, oh, you want to do a syswrite? No problem. Where are you writing it from? Okay, I got that. What are you writing? Okay, I got that. How long am I going to keep writing for? Okay, I got that. So now the operating system will write it to the screen. So at this point, you'll see hello world on the screen without you having to do all that heavy lifting behind the scenes. All we really did here is move 4 values into locations, even though it looks scary. Then what's this guy? Notice we're moving something into the same location, RAX, as we did up here. But in this case, we're putting in there the number 60, magic trick 60, which is actually sysexit. Different magic trick. And for sysexit, it actually needs 1 input, the one in RDI. And it allows you to output a like a success code. Usually a 0 means everything went to plan, a 1 means something screwed up, and you can actually have even other values if you want to have different kinds of error codes. But usually we wouldn't even use this. So this sysexit just requires that secondary value. So we're going to say, OS, we want you to call magic trick 60, which is sysexit. Everything went fine, so I'll put a 0 for the 1 input you need, and then call the operating system. Operating system will look at RAX, see that, oh, you want to do a sys exit? Did everything go to plan? Yes, it did. Program's over. That is hello world in Linux assembly. These first lines of code and the second lines of code effectively behave the same way. We're just calling two separate system calls. So this code leverages the operating system's power tools. All right. Questions about that? Keep in mind, I'm not going to test you over this type of stuff. I'm not going to ask you to write this. So at the high level, do we pretty much see what's going on here? All right. Now, if I gave you an option for your career and I said, would you rather write zeros and ones all day long? Or would you rather directly talk to the CPU like we did up here for writing one character at a time? Or would you rather use the operating system as a power tool? But those are your only three options. Which one would you choose? Obviously, this last one, right? Okay. It's getting us closer and closer to something we can tolerate. And for a long time, this is the code computer scientists would have written. Okay. Keep in mind, the programs we're writing were simpler than the programs we write today. We've become very good at making our computers do all sorts of cool stuff. So we need more and more powerful tools. All right. So the punchline here is that even though we feel like in a pinch we could tolerate this, we probably still want another layer between us and this that will write this for us while we write something like printf hello world, one line of code. We do printf hello world, we run it through some tool called a compiler for C++. It turns it into this. It then turns it into zeros and ones, going through the assembler, ultimately links it to create an executable, and then we got hello world on the screen. So a human being wrote one line of code. Actually, it's more like 4 lines of code because you have to write it in a function, but very English looking code, better than this. So we effectively write a single line of code and all of this magic happens behind the scenes. That sounds even better, right? That is where modern day computer scientists are going to live. You're still going to be working with coding languages. Pretty quickly, you're going to realize these aren't that difficult to work with after you get an appreciation for what these languages are doing. But always remember, this is what's ultimately happening under the hood for you. Make sense? All right. So next class, we're going to come in here and we're going to talk about how do human beings solve problems, how every single programming language has facilities for those ways human beings solve problems, and then what the equivalent is for a programming language. These 2 slides prove to you that all you need to do is learn how to program. Once you know how to program, you could pick up any programming language in a weekend. All right? All right, I'll see everybody on Tuesday, and I think the roof work is done by then. Yeah, we're meeting in this classroom moving forward. Hopefully less glue smell and less, well, I could deal with the glue smell. What's up?
For the place values, when you're